In Allegro Sample 2, we created a simple function that drew a colored rectangle of a specified width and height at a certain point on the screen. If you fiddled with the parameters of this function and created a rectangle of a large size, you'd have noticed that it's actually a very slow process. That's because manipulating individual pixels on the screen can be an inefficient process. One way we can speed things up is to use actual images, such as bitmaps, instead of trying to alter pixels directly. Graphics cards and libraries have special functions for drawing whole images, which is faster than drawing pixels one at a time, since we only need one operation to draw our data to the screen. Images can be stored in many different file formats, such as BMP, JPEG, PNG, and GIF. BMP files are the largest type of image format, since they use no compression at all. They store pixel information with 1 byte of information for each of the 3 color channels, so they typically don't support transparency, or alpha. JPEGs use 1 byte per color channel too, but they also support various levels of compression. This can significantly reduce the file size, but it can result in a loss of data. Usually, humans don't mind too much, since JPEG compression is optimized to get rid of the less important data first. A properly compressed JPEG image can be easily indistinguishable to our eyes from an uncompressed version. JPEGs also don't support transparency. PNGs again use 3 bytes of color information per pixel, but they can go up to 4 channels, allowing for a transparency or alpha channel. GIFs use a palette system that allows for the selection of one color from a predefined set for each pixel. The palette allows for 256 different colors, each of which uses 3 bytes. One of these colors may be transparent though. In Allegro and many other graphics libraries, the word bitmap is used for any image, regardless of the file format. The first step in using a bitmap in Allegro is to include the related header file, the image add-on. Then, in our initialization code, we initialize it. Once that's done, we can start loading and drawing bitmaps. Note that these are 2 distinct operations. First, we need to create an Allegro bitmap pointer. Again, we'll talk more about pointers later. We initialize the bitmap to the value returned by the function al_load_bitmap, which we provide with the file we want to use. If our image doesn't support transparency, then we can assign a color to treat as transparent, using al_convert_mask to alpha. We provide the image and a color using al_map_RGB. This exact color, if found anywhere in the image, will not be drawn to the screen with the rest of the image. Previously in main, we called drawRectangle. Now we'll call al_drawBitmap. We'll give it the name of the image we want to draw, as well as where on the screen we want it to show up. Additionally, there's another parameter for controlling some possible effects. For now, we'll leave that at 0. As we talked about in the previous video, just as related code can be grouped together into functions, so too can related data be grouped into structures. In Allegro Sample 2, we had our drawRectangle function, which took 7 parameters: the x and y of the rectangle's top left corner, the width and height of the rectangle, and the R, G, and B values of its color. This is very unwieldy to say the least. If we want to use many different rectangles, we're going to have a real mess on our hands when each one object is composed of 7 different elements. So let's look at a way to organize it better. We want our rectangle to be a structure, so we can refer to its constituent parts collectively, rather than individually. So we start with that. Struct rect. rect for rectangle. Each structure consists of a bunch of member variables, and each of these variables has its own type and name. Together, these members contain all the information necessary to describe a particular object or entity in the program. In this case, our structure should contain all the information needed to describe a rectangle. So we'll have our 7 integers, an x and a y for position, a w and an h for size, and r, g, and b for color. It's worth noting that Allegro uses structures extensively itself. We've worked with many of them already, including Allegro Bitmap, Allegro Display, and Allegro Keyboard State. Remember, structures create a new, complex data type in the program that can be used just like a standard data type to create variables. In our example here, we'll use RC as the name of our rect variable. Members of a structure are accessed through the structure itself, via the structure's name and a period. rc.x refers to the x value of our rectangle, and rc.g refers to the green color channel, etc. We can now easily create more rectangles using our structure, and each of them will have their own x's and y's and so on. We can easily amend our drawRectangle function to take a rect instead of that ghastly sequence of 7 integers. We can create a structure for our bitmap in this fashion too. A bitmap has 3 pieces of information in our code: the image itself, the x and the y coordinates at which it needs to be drawn. As with the rectangle, we can group this together and make a game object. Game object will have our Allegro bitmap pointer as well as x and y ints. Comparing our 2 structures, rect and game object, we might notice that the bitmap really just replaces the color and size information of the rect. We can quite happily have a function that draws a game object just like our drawRectangle function. drawObject needs to take a game object as a parameter and work with that. In the code, we won't have much, just one line. al draw bitmap, which will provide with the object's bitmap, x and y. Simple. We've just made the process of drawing a game object much simpler. Now all we need to do is pass in whatever object we want to draw to the screen to our function, and never mind about all the other parameters. Allegro provides functions similar to standard C++ for writing text to the screen. The first step in writing text is to load in a font. Much like bitmaps, we can't write anything if we don't know what it's supposed to look like. And like working with images, we need to include another couple of add-ons. In this case, Allegro Font and Allegro TTF. The font will be stored in an Allegro font pointer, which we'll call gfont. After initializing our font add-on by calling al init font add-on and al init ttf add-on, we can load a font into gfont in one of 2 ways. We can call al load ttf font followed by the file name of a TrueType font file as well as the size of the font. Another option is to use al load font followed by the file name of a fixed font, such as a Targa file. For a fixed font, the size is not relevant. As with bitmaps, there's another parameter, but we can leave that at 0. The most frequently used function to write text in Allegro is al draw textf. The first parameter is a font, followed by color, x and y coordinates, and another irrelevant one. The last parameter is a printf-style text string. We could print some information, such as, say, a game's score, by writing in quotes, score is %d, score, assuming such a variable exists. As we mentioned earlier, individual pixel access functions, such as ALPutPixel and ALGetPixel, are very slow operations, since they access graphics card memory directly, rather than system RAM. To speed up the process of drawing an object, we used bitmaps. This sidesteps the problem, but it doesn't really address it. Now we're using pre-existing images to draw to the screen. Ideally, we still want to manipulate the pixels that are being displayed. An alternative method that does address this problem is to create a copy of the bitmap being displayed and perform our pixel operations on it in system RAM and then send it back to the graphics card. This is called locking and unlocking. If you take a look at Allegro sample 3C, you'll see a new version of Draw Rectangle. In it, we get the current target for ALPutPixel. This can be any bitmap, but the default is the screen. ALSetTargetBitmap can be used for this purpose. We then lock it, meaning we copy it to system RAM. There we perform operations and modify the copy. Since this is done in RAM, it's much faster. Finally, we unlock it, which sends it back to the graphics card. That's it for this module. We'll meet again in the next one.